Welcome back, everybody. So we are here to hear the last lecture in the lecture series of Marco Antonio Vincentelli, who lecture on degenerate automorphic forms and Euler systems. Yeah, go ahead.
Thank you so much again. So thank you all of you for bearing with me until the end. So the plan for today's talk is going to be to go beyond Eisenstein series. That is to treat another class of what we have called so far degenerate automorphic forms. And I will treat the case of GL2 theta series. Okay, so the plan for today's lecture is first I will talk about the motivation and setup. Then I will talk about the construction of these theta classes. And then I will talk about some applications to these constructions. And if time allows, I will finish with some speculations. Okay, so roughly this is the plan for today's lecture. So let me start with one. So throughout P is a fixed prime. And now let me consider F a cuspidal Hecke eigenform. And I will denote by rho F the Galois representation attached to F by Achter and Shimura. I will assume that F is actually weight 2, just for simplicity, attached by Achter and Shimura. So rho F, I normalize things so that rho F, I see it as a quotient of the first étale cohomology of the modular curve with some level. And then, so here the coefficients should be L of 1, where L over QP is a finite extension containing the Hecke field of F. Okay. And so this is a Galois representation of GQ. And so in the examples I treated in the previous lectures, in the first one that also Chris explained, Kato built an order system for rho F seen as a Galois representation of GQ. And now the point of this talk is to try to understand what happens when we view not rho F as a Galois representation of the absolute Galois group of Q, but as a Galois group of K. Where K over Q is quadratic imaginary. So the point of this talk will be to build the relevant classes to construct an order system for rho F, but seen as a Galois representation of the Galois group of K. And moreover, try to explain is there a relation? So another question is there a relation between such an Euler system. And so this is an Euler system over K and Kato's Euler system over Q. Okay. If any, because here we're just considering the same Galois representation, just we're seeing over K instead of over Q, over Q. So one of the key example, which are the first sort of historically significant example, was just when you consider the Galois representation ZP of 1 with the Galois action of GQ, then the relevant Euler system, as we've discussed, was the cyclotomic units Euler system. But if you consider rho is still the same Galois representation, but with an action of GK, then the Euler system is the elliptic units Euler system. Yeah. And there is a paper of Gross proved a precise relationship between them. Between this Euler system. I won't state exactly what this relation is. Just let me say that this relation is an algebraic avatar of the factorization of L functions of complex L functions, which is the following. So if pi is the automorphic rep generated by F, pi k is its base change to k, and let's say chi is a finite order Hecke character of k factoring through the norm, so really coming from Q. Then you have this relation that if I take the base change of k and I tensor it with chi, and here I take s, then this factors. So I get L pi tensored with chi seen as a Dirichlet character of Q, s times L of pi tensored with chi epsilon k over Q, s, where epsilon k over Q is the character corresponding to k by class field theory. Okay, so we would like, so the point of this project is we would like a similar oops. So here I stated the factorization in the case where pi was the one generated by F, so in the GL2 picture, but obviously in the ZP1 case, this is just the factorization of the Dedekind zeta function. Sorry, but so this is we would like a similar relation of Euler system that um, um, expresses algebraically the factorization star. So I call this relation star. Okay. So this is sort of the motivation is try to have a very similar picture than cyclotomic units, elliptic units, Kato's Euler system, and then another Euler system. Okay. So now the question is where to look for this Euler system over K for rho f. And so from the diagram of the first lecture, sorry, this was the second lecture, but my first lecture of the second lecture, we want to find an integral representation of the L function, L pi k tensor chi. And this is given by the Rankin-Selberg integral. Selberg integral. So that is, say chi is finite order, then L of pi chi, the base change of chi tensor with k s is the same thing as the L function of pi tensor with the automorphic induction of chi. So this is an automorphic representation of GL2, which is the one generated by a theta series. And so I can write this down as the integral of an Eisenstein series with the parameter s times the theta series attached to chi. This would be a weight 1 form, and then times f, my weight 2 form. And this happens on GL2. Okay, so this was my period integral that should motivate the construction of the order system. Okay, so now there are actually two ways to interpret such an integral. So this integral. So the first one is the push forward way. What does it mean? It's to just say that the degenerate automorphic form that appears in this integral is just the Eisenstein series. Push forward way. Only the Eisenstein series is degenerate. And so immediately it becomes a push forward integral in the sense that the degenerate automorphic form is on the small group. So from the point of view of before, the small group is GL2 with my Eisenstein series on H on the small group, which lies inside GL2 times GL2, and my non-degenerate form is just my theta chi times F. And so from the point of view that I explained in my second lecture, you should push forward an Eisenstein series to a product of modular curve. So the key word here is push forward to a product of modular curves. And this is exactly the point of view that is taken by Ley, Loeffler, and Zerbus, which you may or may not be familiar with. Exactly the point of view of Ley, Loeffler, and Zerbus. So, and indeed, they construct an Euler system for rho f over k, but the issue is that they cannot pass through the central character. So there are multiple issues. So issues with this approach. So so you cannot compare to Kato because in the construction they need the theta series, at least the Galois representation attached to the theta series. So it's just the induction of from k to q of chi to be residually reducible. Yeah. It's because uh, residually irred. need that. Okay, and also this only treats the case of the ordinary f without denominators and split p in K. Okay, so these issues, at least for ordinary f and the fact that they cannot pass through the simple characters, so these issues are partially resolved by Burungale Skinner Tian 1. But they only construct the base class of an order system, or what they conjecture to be the base class. They only construct a base class or a zeta element, or also known as a zeta element. Okay, and still P needs to be split. Okay, so now you would have guessed it, there is a second way in which to interpret this integral. So another way E theta chi f so this is to say that, and this is the main idea of my thesis, of the second part of my thesis, is that theta chi is degenerate. Okay, so now the degenerate automorphic form is not just E. But E, so sort of E times theta chi on GL2 times GL2. Okay. And the non-degenerate one is F on GL2. So this Rankin-Selberg integral becomes a pullback integral. So becomes a pullback integral. Okay. So the point is that now you should construct classes attached to an Eisenstein series. So E times the theta series. Okay. So this will be the point of view that I will take in this lecture. Okay, so just as a remark, compare to Kato's approach, which the relevant integral is now a product of two Eisenstein series against f, which is basically the L function of f. So maybe I should write pi. And the degenerate automorphic form here is clearly the product of the two Eisenstein series. So it is a pullback integral. Okay, and indeed, Kato pullbacks the cup product of two modular units, which are avatars of Eisenstein series, to a diagonal copy of a modular curve. Okay, so the idea is simply now to replace an Eisenstein series with a zeta series. Okay, So this is the main idea. But for this, in order for this to work, you do not have modular units, but you need to construct canonical étale classes corresponding to this theta series. Okay, so this leads me to the second part of the talk, which is going to be about theta classes. Okay, so here P splits. Okay, actually in my thesis, P is inert because I thought it was the most interesting case, but it turns out also the P split case is quite interesting, and this is due, this remark is due to Ashay, really. So this will appear, this construction will appear in joint work with Ashay. Okay, where we build this Euler system and derive arithmetic consequences. Okay, so first let me introduce the Siam family, the relevant Siam family, the relevant Hida family. So first of all, let me introduce some notation. Let me write that P times the ring of integers of OK is going to be P times P bar. And let me fix an embedding of Q bar into QP bar, which induces the p-adic complete, which induces the completion of K at P is QP. Okay, so it induces the p-adic topology and not the p-bar-adic topology on K. So now some notation for Iwasawa algebras. So let me denote by K infinity to be the ZP squared extension of K. Okay, and then K infinity V is the one that's unramified, ZP extension unramified away from ZP extension unramified away from V, where V is either P or P bar. And now the Galois groups, gamma K is just the Galois group of K infinity over K. Gamma KV is the Galois group of K infinity V over K. Okay, and then obviously the Iwasawa algebras are the completed group algebras of respectively gamma K and gamma V. Okay, and last notation, the reciprocity law of Artin, or reciprocity map, which goes to the abelianization of B, arithmetically normalized. Okay, so this is it's just a bunch of notation. And now let me just finish by introducing one last piece of notation, which is the character tau v, which goes from AK cross times K cross to gamma, sorry, to GK ab, and then GK ab, this is by the reciprocity map, and then GK ab goes to gamma K of V. So this is the tau v, and then I denote by tau v brackets the universal character, so it's just AK cross times K cross to gamma K of V, so tau V, and then looking at this as units inside lambda K of V. Okay, so now I've introduced all the relevant notations to define the theta family, and so I denote by theta is going to be the sum over n greater than 1, a theta n, q to the n. So this is the q expansion of theta as a Hida family, and the expression for a theta of n is the sum over ideals inside OK such that P does not divide A, and the norm of A is little n, of tau V of x of A, where x of A is an element of AK cross, which corresponds to A. Okay, so this is the usual family of ordinary theta series. So UP of theta is theta. So usual ordinary family of theta series of theta series or CM family. Yeah, of CM forms. Okay, and we will be interested in the weight 2 specializations of this family. So if psi is a finite order character of gamma kV, so psi is to QP bar cross finite order, I can consider theta of psi, which is going to be the following expression, sum over all the ideals as before, of tau p of xa times psi of xa, and then q to the norm of a. Okay, this will be the q expansion of the theta series in weight 2. And so we want to build canonical classes in H1 et al. X1 and p to the r zp1 corresponding to theta psi. Okay. So this is the objective. So it's the same objective that that Chris completed in his first talk in the first talk, where he constructed these classes attached to GL2 Eisenstein series, and now we want to do it for theta series. Okay, so from the point of view again of my diagram, so the key point is need to find geometric reason for why the parameter of theta is degenerate, in the sense that it is smaller than what it should be. The Gauss representation has much smaller image than a normal cusp form. Okay, so why is this the case? So we saw that for example, recall for Eisenstein series, the reason is that they came from the boundary. They were determined by the boundary. Okay, and so now what is this analog of this reason for theta series? And the point is that they are CM forms. So what does this mean is that if you see them as differentials on the Jacobian, they correspond to pieces of the Jacobian that have CM or that have extra endomorphisms than usual. And this extra endomorphism, one of the key thing that they imply is that the Hodge state decomposition of these pieces these pieces splits algebraically. So over a finest extension of say Q. Okay. So and so it's this sort of point that underlies the entire construction. Now, this has a very concrete realization that can be stated in quite simple terms. So the concrete realization of this fact is the following, is that the Galois representation attached to theta psi is rho psi, is the induction from k to q of psi times tau p. So let me call this character chi, okay? So this is the induction from k to q of chi. And so if I look at rho psi and I restrict it to gk, then this is just chi plus chi conjugate. But so if I identify k completed at p with qp, then I get that rho psi restricted to gqp or gkp is just chi plus the trivial character, because k conjugate is trivial at p. Okay. Okay, so this is the concrete description that we will need. Concrete, sorry, consequence of the fact, of the geometric fact. Okay, so now that we have this fact and that we know what we have to do, we can begin the construction. So let's say theta of psi is nu of level gamma 1 n p to the r, and let me denote by pi the map from xn p to the r down to x1 n. So this has a smooth model x1 of n over zp. Okay, so np does not divide n. So as before, and now we can construct. So from yesterday's lecture, we had this Faltings map that compared coherent cohomology to étale cohomology. So we have this map H0 of x1n from the Faltings lattice, which I called last time, tensor the pi star of zp, going to, so this is tensored with mcp, the maximality of cp, going to the h1 étale of x1 and p to the r, then zp1, tensored with rho minus 1 OCP, where I recall that rho was 1 minus zp for some primitive pth roots of unity zp. Okay, so this is the map which I called Faltings map that I built last time. Okay, so let me denote that after, so again, we know that since theta psi of ordinary, theta psi is a section of this space, so is an element of the Faltings lattice. And so now we say that, let's say that after inverting P, let's assume that theta of psi gets mapped. This is the notation, just the theta psi maps to some element that I will denote by omega of psi. So this is going to be an element of h1 et al. Of x1 and p to the r, zp1 tensor cp. But the map fault is Hecke equivariant after you invert p. So, well, omega psi needs to lie in rho psi. So omega psi belongs into rho psi tensor with CP. So if rho psi, we said that it was what it was the at least restricted to GQP was equal to chi plus the trivial character, then omega psi will be just a sum of, say, lambda times how do I denote it, c chi plus mu times c, where c chi basis of this representation chi, and c1 is obviously a basis of 1. Okay. As of now, I haven't said much of anything. It's just that just by Hecke equivariance, omega psi lies in the Galois representation that's attached to the theta series by Achler and Shimura, and that representation has this local description, just as a sum of two characters. And now the key is also that Falt, so the Faltings map is also GQP equivariant. So this means that since the coefficients of theta lie in a finite extension of QP, let me denote it by say F, then for all sigma in GF, you know that omega psi of sigma is omega psi, but so this implies that lambda of sigma times chi of sigma, C chi, plus mu of sigma, C, is the same thing as omega psi, which so this means that it's just lambda C chi plus mu C. But C chi and mu form a basis, so this implies that lambda sigma is chi inverse sigma lambda, and mu sigma is mu, so this just means that mu lies in my field F. Okay, and lambda now is a period for chi. Lambda lies in CP is a period for chi. But chi has Hodge state 1. At the place above P, right? So lambda cannot exist. It has to be 0. Lambda has to be 0 by the theorem of accent Tate. Okay. So this implies that omega psi is just a multiple of a basis. So it lies in the line, lies in the trivial representation. Okay. So omega psi is fixed by GQP. And since the line fixed by GQP was the one corresponding to the conjugate of the character chi, so you know that omega psi GQ acts on omega psi by the character chi conjugate. Okay. So here we used local information to also deduce global information, because the two lines were the lines where we knew how the global Galois group acted, and we just looked at what it was locally. Okay. And so we know, so now the Faltings map, so by the integrality properties of the Faltings map that I explained before, plus a little bit of extra work, but really nothing interesting, really just basic linear algebra, you know that the Faltings, so you know that, so this was Faltings of theta psi is equal to omega psi, belongs to H1 et al. Of x1 n p to the r with coefficient in zp psi 1, where zp psi is zp adjoint the values of psi. Okay, so this gives us the construction that I promised about the canonical theta classes. So the Faltings map, which comes from coherent cohomology, allows you to normalize certain canonical vectors in the étale cohomology of the modular curves. Okay, so this construction can be made to work also in the inert case But with the important caveat is now certain periods appear. Means that the image of it by defaulting class of a theta series will not lie on the nose, will not be rational on the nose, but it will be this mu here that I defined won't lie in a finite extension of QP that's determined by the character psi, but it will be an actual period. Okay, and so you have to somehow divide by this period in order to get canonical étale classes, and so they're not really canonical because they depend on this period. But so there are better periods than others, but this is another topic. I just wanted to mention that also in the inert case, you can construct analogous theta classes. Okay, so now how do we construct the Euler system? But before going into the actual construction of the Euler system, let me ask if there are any questions about what I've done so far.
Seem to be no questions, so you can.
No question. Okay, very good. So let me proceed. Where is it? Okay. Sorry. Okay. Yeah. So construction of the Euler system. So as of now, we have only variation along k infinity v. So we need to add variation, sorry, k infinity p. So we need to add variation along p bar. Along v bar. And the way you do that is just to add cyclotomic variation. So take central character twist of these classes theta psi. So as to get variation, so get now classes omega psi for psi a finite order of gamma k, character of gamma k. So I'm just saying that you can upgrade the construction that I did before to get classes that are defined over abelian extensions of k, and also you can away from p to get so away from p. Just change the. You can add a tame character. So you would consider something like rather a stabilization. So instead of just P not dividing A, you also impose that N does not divide A, and you would define by the same formula. So tau P of XA, psi of XA, Q to the norm of A. So now this is the omega psi stabilized at the ideals N. And so these are the classes so sorry, not equal. So they come from this theta series. So theta n of psi. So they come from this theta series by this procedure of this Svelting's map. And so these are the crucial classes to build the Euler system. So how do you do that? Well, so you just take this class omega psi of n, and you just cup it with an Eisenstein series for the character psi q minus 1. These are the same Eisenstein series as in Chris's talk. So this will be a class in the H2 et al. Of y1 times y1, so two modular curves with coefficients in z, p, psi 2. Okay, so this is geometric et al. Cohomology. Okay, and now, so maybe let me say, compare with Kato, where he takes E of, say, a character chi over q, cupping with the inverse, essentially. So this is like critical one. This is an ordinary one. So in H2 et al. Y1 times Y1 ZP chi 2. Okay. So it's really parallel. We've just replaced a class coming from an Eisenstein series with a class coming from a theta series, which is exactly what is predicted by the formula with the Rankin-Selberg integral. Okay, so now do like Kato. So lift to absolute et al. Classes. So for Kato, they come as absolute classes because he uses modular units, but you can use our methods to lift them to absolute et al. Classes and take Abel-Jacobi images. Okay, but there's another point of view, which is just use relative cohomology. Both approaches work, but just for similarity with Kato, for example, in this forthcoming work with Ashay, we simply decided to use the Abel-Jacobi map, which simplifies certain discussions. Okay, so this is essentially the construction, the key construction, and so to finish in the last 10 minutes, let me talk about what the main application and state exactly what we prove. So applications. So theorem, this is joined with Ashay. So there exists a collection of classes z, n, and then an integer r, where these classes live. They live in chi, so kn, so this is a maximal abelian extension on ramified away from n, with conductor, sorry, n, and it takes values in the geometric et al. Cohomology of the modular curve, h1n, p to the r, and then here zp2. Tensor, and this is the norm relations at P, is lambda k. So this is the Iwasawa algebra that I defined before. And then there is a twisted Galois action, which is given by, so tau p bar inverse times omega sig. Omega sig, yeah, omega sig. So omega sig is just the cyclotomic Teichmüller character. Okay, so this Teichmüller character comes from the central character twist construction that I said before. But this is where the classes live, and they form an Euler system. So there is a precise relation between zeta of n and another prime. So I won't say exactly what do I mean by this, but it's an Euler system. So, and moreover, so you see that this integer r is the level of the modular curve, and they're compatible under the levels. So there is a class z n infinity that belongs to h1 kn of the inverse limit of h1 et al y1 np to the r zp2 tensor the same thing lambda k of tau p minus 1 omega sig. Okay, so this is basically uh, u, so actually it's exactly the u zp coinvariance of completed Borel-Moore homology. Okay, so you see a very big Galois representations. You see universal deformations of Galois representations when you localize at the maximal ideal of the Hecke algebra that's residually irreducible. Okay, so these have, so remark, these classes have much better p-adic properties than the classes defined with Beilinson-Flach element via Beilinson-Flach elements. Okay, so really this variation, this trace compatibility without taking ordinary projection is very good. And the last thing I want to mention is you get a relationship with Kato's Euler system, a very strong relation with Kato's Euler system. Why? Because in weight 1, the theta series, theta psi, if psi factors through the norm, so if psi comes from Q, is an Eisenstein series. If psi factors through, so sorry, here, let me say theta 1 just to say that taking weight 1 factors through the norm. So this is the key relation that allows us to relate the Euler system to Kato's Euler system. Okay, so this is some sort of Ziegler-Weyl formula, but in the p-adic sense, it's an obvious formula. Okay, so in the last, how much time do I have? Yeah, 5 minutes. I will just give some speculations. So why is it important to go beyond the GL2 case? Sorry, beyond Eisenstein series and also beyond the GL2 case. In this field, to me, one of the key problem is to really try to do the construction of an Euler system for rho f, action of GF, where f over q is a totally real field. And now f is a Hilbert modular form. Okay. So try to do essentially Kato, but over a totally real field. But the issue is that the natural thing to do is to consider GL2 Hilbert Eisenstein series. But then you cannot work on the Hilbert modular variety because then y inside y times y codimension D equals the degree of F over Q. So the key numerology assumption is wrong. So problem with numerology. So Y is a Hilbert modular variety. So there's this huge problem with numerology, and there is also even another problem is that in the cohomology in HD of Y, you do not see rho F, but you see the tensor induction. Okay. So you don't get an Euler system for rho F. So partially this is, I mean, under the Plectic conjectures, this solves these issues. The Plectic conjectures address these issues, but it seems that they're completely out of reach as of now. And so what to do? And so maybe an idea would be to consider xb inside xb times xb, where now xb is a Shimura curve for B a quaternion algebra over F. So now this is one-dimensional and this is two-dimensional. So now the numerology works. But what is the big issue if you do this is that xb is compact. So no Eisenstein series. There is no boundary. So what to do? Well, there still are theta series. So you may want to consider the product of two theta series. And then use the triple product formula, sort of to build this this Euler system. But so this would be an Euler system over quadratic imaginary, a CM extension of F. So maybe this can work, but now you're stuck with how do you check? So now the question is, how do you check that theta series on XB belongs to the Falting's lattice to get something integral? Because you don't have Q expansions anymore to compute explicitly. So this is an open-ended question. If some of you have any ideas, I'll be taking it very gladly. And so I guess I would like to end this lecture series on these questions. So I hope that I have shown that looking at period integrals that represent L functions and then looking at which is the degenerate automorphic form and trying to construct associated étale classes to that degenerate automorphic form is the way to go to build new Euler system and understand better, at least in rank 0, the Bloch-Kato conjecture. So thank you so much for your attention. I'll stop here.
Thank you. Are there any questions, remarks?
I don't think I can hear. Yeah.
Can you hear now?
Yes, I do. Yeah.
Said beautiful lectures.
Thank
For
you.
sure, there is no cusp at infinity, which is used to do the Q expansion, but they are used quite effectively to do things on the Shimura curve. That doesn't help.
So it's really about at some point you need to compute something. So either you have to compute the values of this theta series at a Zariski-dense set of CM points, or you compute a T expansion at some point of the Shimura curve, but you need to show or sort of to have an integral normalization in the family of theta series. And without Q expansions, I really don't know what to compute. Because the computation of T expansions, so this would be like taking the completed the image in a completed ring at an ordinary point. There is no explicit formula for such things.
No,
It
so I was
seems
just asking whether computing them at CM points of the Shimura curve, is that feasible or not feasible, useful or not useful?
so. This is actually the route I'm trying to explore, but but so far I haven't had any success in
All right. I mean, just to go back to your considerations using Eisenstein series, what is the role of what is the role of Eisenstein series? Is it because they have good Q expansion or something else?
The role of Eisenstein series is because they are from an automorphic point of view, they are always almost present when you have this variable s, when you want to represent an L function. And then in order to have a geometric Eisenstein series, you need your Shimura variety to have a boundary. But when you ask for it to have a boundary, then, for example, if you wanted to work with the Hilbert modular variety, our method somehow doesn't work because the numerology doesn't work. And even more seriously, you don't see in cohomology the correct Galois representation. You see the tensor induction. So you cannot use Eisenstein series directly. Sort of you would really like to use Eisenstein series to imitate Kato, but sort of over a totally real field, you can't directly using this method. You need to know more about Hilbert modular varieties, and these are dysplectic conjecture, Nekovar, and Scholl. So the basic idea was to just just then don't work over Hilbert modular variety, but work over Shimura curve and use theta series. And so you would get something over K, and maybe you have some hope of descending it over to F if you're really interested in the Iwasawa theory over F. But now, as you pointed out, you don't have Q expansion, and so you need to characterize the integrality of this theta series on Shimura curves, and it's very hard to do so because you have to compute all these values at CM points. And I don't know how to do that efficiently.
All right, thank you.
Hi. Hi. Regarding to your Hilbert modular forms comments, so can you recover the Ashay representations Euler systems because you have this tensor induction from F to Q, right?
Yes. So again, so that's really a push forward integral. So where you have a GL2 Eisenstein series, and so that is actually done by Ley, Lefleur, and Zerbes.
Yeah, but so you cannot use your pullback method here, or for a Ashay case.
For Ashay case, no. Yeah.
Okay. Thank you.
Yeah, I don't think so. Yeah.
I have a question which is more from the Iwasawa theoretic perspective for the main conjecture. So Euler systems, we are interested because they give periodical functions.
Yeah.
So what does your result translate? What does this factorization result translate in terms of periodical functions?
You mean in the result with Ashay?
Yeah.
So this is a very interesting question because in the ordinary case, you have well-behaved integral, you see, periodical function as element of the Iwasawa algebra. And so in particular, you can give the relationship with Kato's Euler system is something that will be can take the form of when you take the cyclotomic specialization of this Euler system and you take the co-restriction down to Q, that is Kato's Euler system times the twisted p-adical function. Okay, but this is only when you ordinarily project. Now, in the case where you're not ordinary, so this Euler system is for the full cohomology, really. It's for the full cohomology. There are versions of the p-adical functions, but they're not integral. So I really see, and the same thing happens in the cyclotomic versus elliptic units Euler system, where P doesn't split, you still have the relation of factorization of the Euler system, although you do not have the well-behaved p-adical function. So I see somehow this as some stronger, statement as a factorization of p-adical function. I don't know if that answers your question.
Somewhat. Thank you. Thanks. Any other questions, comments? If not, let's thank Marco for his series of lectures.